Okay, so in this segment, what I'm going to show is how we will define our notion of energy. So let's go back and recall how we've dealt with the general topic of work before. Suppose we have a particle that moves along a path. Let's say it's progressing from some point 1 to some point down the road, point 2. So the distance along this path, like before, we'll refer to as the distance along it, s. So let's consider some small interval of time as the particle is moving between point 1 and 2, where our particle traverses a small distance, ds. Okay, and let's suppose that as it does so, there's some net force or some resultant force acting on it, maybe like this. So here's my resultant force, or that is my net force. This is the vector sum of all forces. And if we wanted, we could, of course, consider certain projections of this. We might have here a tangential projection and then a projection perpendicular to that. So this would be the net force, or that is sum of forces in the normal direction, and the net force in the tangential direction. So we know that our particle, as it moves along this path, has a velocity that is tangent to the path. So the particle's velocity here is given by v, and what we don't know in general what its magnitude is, but we do know that it will be directed as shown. Okay, so this tangential component is a projection of the resultant force, and maybe that projection is dictated by this angle theta. So as we've seen before then, the work as I'm moving along from 1 to 2 is given by a whole bunch of these little instants. Okay, so a summation of them, where at each instant what I'm doing is I'm looking at, as I move from one little position to some other position, the inner product of f dot dr. Now this dot product basically guarantees that it's only this tangential piece that we care about. That is, as I've said before, what we care about is the alignment of force and displacement. So first of all, as a little, if you will, definition building towards a bigger definition, we call little building block definitions of this type of lemma. So lemma number 1 for today. Principle of work and energy. As I carry out these integrals, going from some initial position to some new position down the path, really it's just that tangential component. This is what comes out of that dot product. The tangential piece and then the distance ds. We can connect this to a corresponding acceleration using Newton's second law. So we know by Newton's second law that this is equal to, so I'm looking at what is f of t. So plugging in ma for my integrand, leaving the integral alone, as I move from S1 to S2, ma. Now, because these forces are strictly in the tangential direction, it follows that the acceleration will be strictly in the tangential direction, and then ds, as we had on the left-hand side. If we recall from prior lectures, the relationship a ds is equal to v dv. In this case, we have a tangential acceleration, so this special case, a sub t ds is equal to v dv. So I note that I have in my integrand an a ds. So let me make this substitution, changing the integral to the integral, and with it I have to change my limits from some initial velocity to some final velocity m v dv ds dx. Okay, so what I've done is I've solved this for a sub t v dv over ds. That comes into here. The ds carries from what we had on the prior expression. Okay, which just simplifies, of course, to the integral from v1 to v2 of m v dv. So this is an easy integral to work with. If mass is constant, it comes out, and we just have the integral of v dv. So what was all of this? This was what we called the work we do as we go from point 1 to point 2, u1, 2. So then what we have is that the work I do in going from 1 to 2 is given by calculating this integral 1/2 m, and then I've got v squared, but my integral limits I need to take into consideration, so that's v2 squared minus v1 squared. Now you note that on this right hand side, if I were to carry through this multiplication, I would have 1/2 m v2 squared minus 1/2 m v1 squared. So let's pause and make a quick point to define kinetic energy. Definition: kinetic energy. And I don't want to say too much in words about what kinetic energy is. We're going to get to that soon. But for now, let's say kinetic energy is a quantity that's expressed in terms of the form 1/2 mv squared, a familiar notion to all of you from prior physics classes. So if we take this definition, we can go back to our equation here. So let's come back, let's give this thing a name. Let's say that what we had back at this point was equation 1. Let's take equation 1 here and substitute in the fact that these are terms like kinetic energy. Now, these things we will typically denote using T. Okay, so T1 will represent the kinetic energy at point 1, and so on. So we can return and rewrite equation 1 as u12 is equal to this up here. This would be our T2. So T2 minus T1. And just to be clear here, what we're saying is that T1 is equal to 1/2 m v1 squared, and T2 is equal to 1/2 m v2 squared. Okay, very good. So, in other words, if I take T1 and bring it to the left-hand side of the equation, what I have is T1 plus u12 is equal to T2. I want you all to think about what this means. And by the way, we've only considered one particle moving along its own path, but as a corollary, in preparation for things we'll do later, okay, we can take this and extend it to multiple particles. We can have some summation of initial kinetic energies, some net work on that system. Okay, so that would be potentially work done on each particle. So the summation of works in moving from state 1 to state 2 is equal to some final net kinetic energy. This is a very intuitive expression. And what's interesting is that this seems to say that work is equal to a change in energy. And I want you to think about whether that notion actually makes sense. We'll pick up with that in the next video.